When you think about your electric car, or even your air conditioner, or a fancy robot in a factory, have you ever wondered what's happening deep inside? Well, there's this really elegant piece of digital magic at work, a kind of hidden genius called space vector modulation, and it's one of the big reasons why modern electric motors are so incredibly powerful and efficient. All right, let's get into it.
It all comes down to this one central question. How do you get an AC motor to do exactly what you want? I mean, how do you precisely control its speed, its power, moment to moment without just wasting a bunch of energy? That's the puzzle we're going to solve today. So, to get that kind of perfect control, you really need a go-between. Something that can take the steady DC power from, say, a battery, and then transform it into the pulsing, alternating AC power that an electric motor actually needs to spin. And the quality of that translation? Well, that's everything.
And here is our go-between, the voltage source inverter, or VSI. Now, I know this diagram looks a little complicated, but the idea behind it is actually pretty simple. Just think of it as a set of 6 electronic switches that can flip on and off thousands of times a second. Their whole job is to take that nice, smooth DC voltage and just strategically chop it up, sculpting it into the perfect 3-phase AC waveform to drive that motor.
But here's the thing. The inverter itself, that's just the hardware. The real genius, the secret sauce, is in the software. It's in the strategy that decides which switches to flip and for how long. The how of the switching, that's the key to amazing motor control.
So, the old way of doing things was to try and manage each of the 3 electrical phases all on their own. And honestly, it was kind of messy. It's like trying to juggle 3 different balls while you're running. Sure, you can probably do it, but it's not going to be smooth, it's not going to be very efficient. There just had to be a better way.
And of course there is. This is really where the big aha moment happened. Instead of trying to wrangle 3 separate things at once, engineers decided to look at the whole problem from a totally new angle. They basically added a new dimension to their thinking.
And this new perspective is called space vector modulation, or SVM. The core idea, as you can see right here, is to just stop thinking about 3 separate phases. Instead, SVM combines all 3 of them into a single unified arrow, a vector that rotates around in a simple 2-dimensional space. And this image just nails the concept. Forget those 3 messy, wavy lines. Now, all we have to care about is this one single arrow. All we need to do is tell that arrow where to point and how long it should be, and the motor will respond perfectly. It just makes the whole control problem so much simpler.
Okay, so the goal is to create that perfect rotating vector, but the inverter hardware itself has limits. It can't just create any vector it wants whenever it wants. It has a very specific, limited set of tools it can use to get the job done.
Let's call it the inverter's palette. It really only consists of 8 basic states. 6 of them are what we call active vectors. These are the ones that do the work. They have power, and they point to the corners of this hexagon, actually making the motor move. The other 2 are zero vectors. They sit right in the middle, and they're basically a pause button, telling the motor to do nothing for just a tiny fraction of a second.
All right, so you see the challenge, right? The vector we want can be pointing anywhere inside this hexagon, but the inverter can only produce these 8 specific options, basically the corners or the center. So how do we bridge that gap?
How do you possibly make an arrow that points, say, somewhere between V1 and V2? You can't command it directly. This is where the real intelligence of the SVM algorithm comes into play.
So the algorithm follows this very simple recipe, thousands and thousands of times every second. First, it figures out which slice of the hexagon our target vector is in. Then it picks the 2 active vectors that make up the edges of that slice, and it throws in one of the zero vectors. And finally, this is the magic part. It creates the target by rapidly flicking between those 3 chosen vectors.
It's kind of like mixing colors. Let's say you want to make orange, but you only have red and yellow paint. What do? You quickly alternate tiny dabs of red and tiny dabs of yellow. By controlling exactly how long it paints with each of its available vectors, the SVM algorithm creates an average voltage over a tiny slice of time that is a perfect match for the vector we wanted in the first place.
Okay, this all sounds really clever, but you might be thinking, is it worth all that complexity? Oh yeah, absolutely. Let's talk about the payoff, because this is where SVM really shows its massive advantage over the older ways of doing things.
This quote from the Power Electronics Handbook, it just nails the main benefit. It sounds a little technical, but it boils down to 2 huge wins. You get more power out, and you do it with less work.
So here's the bottom line. SVM is just fundamentally more efficient. It's better at using the voltage that's available from the power source. It doesn't leave any performance on the table. It intelligently uses its switching to get the absolute most out of the hardware it's got.
And we can actually put a number on it. Compared to the more traditional methods, SVM can use about 15% more of the available DC voltage. And what that means is you can get 15% more speed or torque from your motor, all from the exact same battery or power supply. And that 15% boost translates directly into things that we all care about, right? It means higher motor efficiency, which means longer battery life in your EV or a lower electricity bill. It means smoother, quieter operation with less vibration. In short, it means better performance all around and way less wasted energy.
So, what began as this really complicated problem of trying to juggle 3 different things at once was totally transformed just by looking at it differently. It became this simple, elegant problem of just creating a single rotating vector. That's really the power of a new perspective.
And it kind of makes you wonder, doesn't it? As our entire world becomes more and more electric, our cars, our homes, everything, the efficiency of every little part matters more than ever. Could it be that these invisible, intelligent algorithms running deep inside all our devices are one of the most important keys to unlocking a truly efficient and sustainable future?